Okay. So since the NERC used the BS or BPS as the main subject to define the criteria. So the basic idea is um, the basic idea is um, to define the boundaries of the power system by which you can ignore or you can the reliability is not that significant anymore. So for instance, um, we are right now in the power system, right, in Tennessee. So there's a Tennessee power system operated by the TVA at a very high voltage level, and under high voltage level there could be some other power system built by, for example, by uh, the Lander City or by the Knox County Utility Board at a lower voltage level and under 100 kV. And there could be some other wires connecting from that transformer to your neighborhood, and from that neighborhood to your house, and from that house to your outlets, right? So all the wires actually connected at the same power system. But for NERC, when we talk about reliability of the system, we cannot consider every single wire, every single component from the generator until the end user. So we have to stop at somewhere. We have to define the boundary for this power system within which is the most significant to the engineer or to the power company. So the boundary usually defined as the where we call the bulk electric system or BPS. Basically, that means the majority of the system and above 100 kV. So 100 kV is a very useful criteria for you to justify whether this is part of the BS or not part of BS. So in many research papers or reports, depend on whether report is from the NERC or from other entities. If it's from NERC, usually NERC will call it the BS. If it's from a DOE or from other like industry, they usually call it BPS. But basically BPS, BS are very similar. You don't have to know the really detailed differences between the BS and BPS. But basically it just means the majority of the power system, including generation, transmission, and the infrastructure above 100 kV. So that's why you can remember BS as just a part of the transmission, sub-transmission systems connecting power plants, major substation, and high voltage transmission lines. So under 100 kV usually is not part of the BS or BPS. Okay, so starting from now, so all the reliability concerns are mainly focusing on the BS or BPS. So in the future, if you have chance to work at any power company or you help power companies do some consulting studies, so you get their system model. So when you open the system model, there will be a list of all the substations. So if you pay attention to the voltage level of the substation, usually it's pretty much above 100 kV. So if you see any buses with voltage such as like 30 kV, 20 kV, they could be power plant, right? Because we mentioned in power plant, they can operate at lower voltage. If you remember this slide, right? So generators generating electricity at usually lower to 25 kV, then they go through a step-up transformer to the transmission. So BS or BPS basically just means if I draw a circle, basically it means pretty much generation, transmission, right? And also sub-transmission, pretty much this portion as BPS or BS, right? So that's a reliability criteria to apply. Okay, move back. All right, so next we'll quickly introduce how NERC enforce the reliability criteria in the US and also including Canada for the entire the North America. So there were several levels. The NERC defined first level is defined as interconnections. Interconnection means just AC power grids. And the next level will be regions. So within each interconnection, there could be regions. And within each region, there could be coordinator. So we start from this map. This map is about the ISO and RTO we have talked about. That's the regions where fully deregulated electricity markets implemented, right? So you see some regions you have ISOs, which independent system operators who don't know any facility of the system, or some other areas without full deregulation. There are still power companies such as TVA, right? So Tennessee, so they operate a system in that area. Okay, so they all have to meet those three levels to enforce reliability. Okay, so this map is more complex, but it's still about North America. So first, pay attention to the gray boundary, which partition the entire system into 4 portions. On the left, that's called Western interconnection. On the right, the largest one, which is called Eastern connection. So we are actually located in the Eastern connection. And also there are another 2 smaller interconnection. One is called ERCOT or Texas interconnection. That is pretty much a Texas state. And another smaller one is Quebec interconnection, which is pretty much a Quebec province in Canada. Okay, so those are the 4 interconnections. Each interconnection is, physically speaking, just AC power grid. Between interconnections, there's no AC power lines. There are only DC power lines. Okay, so in the US, there's no such a single like national power grid. There are only, literally speaking, there are 3 power grids in the US. We have Western connection, Texas connection, and Eastern connection. So each connection is an individual power grid. So on this map, I also show some peak loads for different connections, such as the Western connection is 168 gigawatt. That's data from 2024. The largest one is the Eastern connection, which has 574 gigawatt. That takes 66% of the entire North America. And Texas interconnection has 10% of the total load, which is 85 gigawatt. And Quebec has 43 gigawatt. It's the smallest one. So those numbers, just think about in the first lecture, I talked about in the next few years, there will be the hyper large scale data centers being interconnected to the power system. So the large hyper data center, such as the one just started operating in West connection by Tesla, I guess. Yeah, that the size about 1 gigawatt, right? So that's so in the next 5 to 10 years, there's a forecasting there going to be more than 10 gigawatt load for data center. So 10 gigawatt load is pretty much, right? If you think about many data center, if it's in Western connection, that take about like 5% of load. So if even more, that actually bring a large load increase over the entire US. So that could be some impact to the power grids in North America. So then you see the colors inside of each connections are not just the same one, but they have different colors, which means because in the eastern connection is too large, so there's the next level, which is the region level. The regional level, so there'll be reliability entities. So which means each reliability entities is responsible for developing and enforcing the reliability standard in that region. So the standards between different entities may not be exactly the same. But within each region, because they have the same very tight interconnection and they have the same very similar situation, so they can apply the same set of standards. So take a look at the regions. For instance, this FRCC, the Florida Reliability Coordinating Council, that is the region in Florida, mainly in Florida. And so this origin one is here. That's IMRO for the Midwest area. And NPCC is for the Northeast Power Coordinating Council. And RFC is actually in this area. And ICRC is actually where we are currently located, including Tennessee. That's for the Southeastern Electric Reliability Council. SPP is actually for Southwest region. And WCC, this is West Connection, right? That's entire West Connection itself, although it's very huge, but it's operated as enforced by one council. And Texas itself is one council. So all the entities listed here actually could be a non-profit corporations. So they can be actual companies existing to enforce the reliability in that area. Okay, so next I want to bring this map. This map has smaller areas, a more smaller area compared to the second one. So this is the third level at the coordinator level. So NERC also define reliability coordinators, which are actual companies. They usually need to have control room monitoring the system in that area. So that is different from the regional level. Regional level, they only just need to be corporations. They define the standard, enforce standard, mainly on the planning purpose. But the coordinator is more in the real-time actions. So they need to have control room to enforce the reliability standards in that area. And this is mainly done by one company. So the logic here is, so for a specific region, okay, if the region is too large, for instance, I'm talking about ERC, that region may have several power companies. For instance, there's TVA is in that region. TVA itself is an individual company. So TVA will be responsible for doing the coordinations in that area. So you see this, that's pretty much the territory within which TVA need to coordinate for reliability. And in the south, there's a southern company, which is another reliability coordinators. So difference between the third map and second map. So third map, usually they need to be a individual company responsible for the real-time coordination. So the logic is, if there's already large companies operating the transmission system, so that company will become the coordinator. So that company can be system operator, like for example, in this area, in the first map, right? PJM is actually the market operator in that area, the system operator. So PJM will become reliability coordinator in the similar area. So if you compare the shape of the map, which don't match exactly, but they pretty much overlap a large area. So PJM as the market operator will determine the market. And for the reliability, it also responsible to coordinate reliability for a similar area. TVA region is not a fully deregulated market. It's but it's regulated system, but TVA will be the reliability coordinator for that area. And for some other area, they actually can tell similar story. For instance, The SPP is the market operator in the southwest region. And on the coordinator will be a reliability coordinator. But the area, you see some area they may have coordinate more region, slightly different from the first map, but basically pretty they're highly similarities. Each reliability coordinator need to have the control room. There will be people monitoring the system stability, reliability, and take actions when it's needed. Any question? All right. So next map has even smaller regions. This is called this map is called it's about the balancing authorities. Balancing authorities. The idea is so if we go back to reliability coordinators map. So if some reliability coordinator is still pretty large, right? So we may further partition that region into a smaller area within each area, and the generation load need to be balanced in real time. Okay. So for smaller area, that coordinator itself may become just one balancing authority. So which means within that area, the generation need to be equal to load all the time. But if that area is too large, you may further partition that area to smaller balancing authority. So each bubble in this map indicate one balancing authority. So TVA itself is operated as one balancing authority. So which means within this region, the TVA has flexibility to dispatch the generation, but within this boundary, the total generation and total load need to be equal all the time. For some large area like Western connection, there's so many balancing authority because the situation could be more complex and there are more smaller power companies, so each company on its own can be balancing the load locally. Okay, so why I want to bring this concept, because later when we talk about the frequency regulation, we have multiple levels of frequency regulation starting from the governor level, which means each generator need to take some action to respond to the frequency. Also, for each region, you need to have a regional frequency control by automatic generation control, AGC function. So that AGC function need to exist for each balancing authority. So each balancing authority need to at least have some generator implementing the AGC. Okay. So we'll talk in more detail about the modeling of the frequency control in each balancing authority in the frequency regulation session. One thing I have to explain here is so when we talk about balancing the generation resources with the load requirements, the generation and the loads can be both physical or virtual. By that, I mean, so for any region, just think about like if there's a smaller region and the total load in this area is much higher than the generation capacity. So that doesn't mean this area will not meet the requirement. The area can purchase electricity from a neighboring area, from Tennessee or from other area. So the generation is also considered the generation, but that purchase generation usually will depend on time, depend on the market, right? You can buy like day ahead electricity or maybe real time electricity. Once you purchase that electricity, that become part of your generation. So the balancing authorities criteria require all such region need to be balanced in real time. So if you predict your load is going to grow and higher than your local generation, you need to purchase electricity. If you know the load will decline and you have more generation, you can sell electricity. But then, or maybe you can just reduce the generation output of your power plant. But you need to keep the balance. So in reality, all the balancing authorities are actually connected, and at the boundary they may have meter. The meter will measure the energy flow, a change between the balancing authority. So in the control room, there's a one set of table which is called a balancing authority table. There will be folks sitting there. They try to monitor the energy exchange between those regions, between those areas, and so such signal will be utilized in the what is called aero control arrow ACE. So this one will be considered modeled in the frequency regulation session. So we will come back to this concept later. Okay. So we have introduced multiple levels of reliability coordinations managed by NERC, but it doesn't mean today's power system is perfect, right? So we from this table we see the power blackouts, which usually means many customers in large area, extended area, lost their electricity for a long time, for extended time. So such blackout event happened after several years. So we still cannot fully prevent such a large blackout from happening. The table started from shows a blackout starting from 1965. That is the first large power blackout, probably the most famous one in the history. So that's also why the NERC was founded. NERC was founded in 1968, right? 3 years later after this blackout. So they realized we really need to study the entire power system as the single single object and to define some standards for power company to apply to comply with. So there are some blackouts actually in North America. I will talk about some of those blackouts in the later sections. For instance, like this in 1961, there are two blackouts that happened in Western nation. WSCC, just the same as WCC, just the older name for WCC. WCC is especially for Western Electric Coordinating Council, right? That's just Western nation. That's an international-wide blackout. There are two such blackouts. Both happened in 1996. The one happened in July was about the voltage stability problem. And the one happened in August, one month later, that was caused by system oscillations and transient stability. So we'll talk in more details about those two blackouts when we move to those sections. Another very famous one was actually 2003 Northeastern power blackout that actually impacted 55 million people, right? That the blackout lasts for at least 2 hours. For some area, that was 4 days. So this is the blackouts very important to me because I was doing PhD in 2003. And my research topic was how to prevent a power blackout. So it was the right timing to me, right? So actually some faculty actually joking about we need to have blackout every maybe several years. Then the public realize the research on power grid reliability stability is really important. Another reason why is 2011 that happened in the San Diego area near the border to Mexico. That actually also impact a lot of people. And there's some other very large blackout in other countries of the world, such as 1999 Brazil blackout that is studied a lot. That called system islanding. The entire system partitioned into several areas and operated as independently. In 2003, there's an Italian blackout, and 2006 is a European blackout. 2012, there's a very huge India blackout that actually impact most of the area of the India. And this is interesting. Ukraine blackout that's caused by some cyber attack. And another reason why is actually also in the South America that impact many countries. Another most recent one is the European blackout. All right, so I didn't include that in the table, but there are a lot of ongoing study on those blackouts. So if you draw the impact of those blackout on this chart, so when you increase the duration, if the resolution time to bring the system back, that take longer, and the customer impact will be huge. So usually, for us, we need to first study how to prevent those blackouts from happening. Second, if they happen, we need to know how to mitigate the blackout, how to bring the system back. So this course will focus on how to study the reliability issues to prevent such a blackout, and also what control action we can take if the blackout has been initiated. Okay, so let's continue talking about reliability. So based on the NERC standard, the reliability of the BS, about electric system, so they need to be reliable. So reliability defined as some requirements, and so first we need to, but it's also you need to keep the balance between the a reliable electric grid and the economical electric grid. So power systems should be built and operated to achieve a reliable electric power supply at the most economical cost. So what does this one mean is, so reliability and economical performance or cost actually are two indices. They're not pointing to the same direction. Sometimes there may be a contradictions between those two. Which means if you want to build a power system that's 100% reliable, that can be very expensive. Okay, so it's not affordable. But if you want to make a grid to be very has minimal cost to operate or largest benefit profit for the utility company, the reliability could be very bad. So we need to find a good balance between the reliability and the economical cost. Then we need to define what reliability we want to achieve. And also we notice when we talk about reliability, we also need to consider some the time period, right? So we can say the system is overall reliable for the whole month, so for the whole week. But and we can also say that the system is reliable now, right? So we also need to define the time period. Then there will be two terms we need to define. The first term is about adequacy. Adequacy is more from the planning point of view. The adequacy is defined as the ability of the electric systems to supply aggregate electrical demand and energy requirements of their customers at all time, taking into account scheduled and reasonably expected and scheduled outage of system element. So anyway, so that is from a planning perspective. So if I have a power system, I want to make sure my generation capacity or my controllability, everything, all the resources are adequate. The total generation is much more than the total load, such as when the load grows or fluctuates, I will never encounter any shortage of generation. So that's adequacy from a planning point of view. Another term is called security. Security is more from an operational point of view. So security is defined as the ability of the electric system to withstand sudden disturbances such as electric short circuits or anticipated loss of system elements. So that look at a smaller or shorter time frame. Okay, That is more from the operational perspective. So one example or one analogy to give you some idea on the difference between adequacy versus the security, such as after you graduate, right? You get a job offer. The job offer is about the $200,000 per year. So when you sign the offer says you're going to receive a salary for $200,000 each year plus bonus, right? That sounds like a pretty good offer as like fresh graduates. So you just take the offer and sign, you get a job. But once you get a job, you also get more information. You didn't pay attention to look at how often you're going to receive your paycheck. They will realize, okay, the paycheck says, the offer says there's one sentence saying you're going to receive a single paycheck at the end of the December. So you start working in January, but you have to wait until the end of the December to receive your first paycheck. Okay, so for that case, I would say your job offer is pretty adequate, right? You get adequate the salaries for all your expenditures, but it's not very secure because you have to think about how you can get through the first 12 months. If you have some money in your bank, you can utilize to go through this entire 12 months. You'll get your first paycheck, then that'll be fine. So that I would say this job offer will be an adequate offer, but not very secure offer, depending on you how much resource you have. So that's one example to give you some idea. Come to the power system. As a planning engineer, they need to define the reliability from the adequacy point of view, right? They need to make sure they have enough generations to power even the maximum load through the entire year or maybe next several years. Your transmission lines need to be strong enough to carry very heavy power flow under even the worst situation. So you need to be prepared for anything, and then you utilize your budget, try to upgrade the system or add some resource to make system be adequate. But once you build a system, and as operator, they need to face any events that happen on daily basis. So if my system is planned for any like outage of losing any power plant, if I lost any power plant, my system should be reliable. But today we get some hurricane or winter storm. I suddenly just lost two power plant. That's not planned. Then my system is not secure. So you see, so the two concepts is still not matching exactly with each other. So in this course, we want to cover both the adequacy and the security problem, including both operation and the planning. Okay, so what are the requirements for reliable electric power service or power system? Usually we expect voltage and frequency to be held within very close tolerances or limits. For our AC power system, usually the frequency is near 60 hertz, very close to 60 hertz, and voltage depend on the which voltage level you're operating this equipment. The voltage need to be very close, like very close could be maybe 2% or 5% difference from their nominal value. And for all the signal generators need to be running in parallel and to meet the load demand. And another term is called integrity. Integrity means if you're operating a power network, the power network need to be fully connected. You may temporarily lose a single line, but that line doesn't break the system into many pieces. It's still a single integrated system. So how are reliability standards used in reality? So in the planning stage, the planning engineer look at next 5 years, 3 to 5 years. So they will try to make sure they meet all the reliability standard when they plan or design, upgrade the system. So based on their planning, the standard should never be violated in the design system. So they need to consider sometimes the worst scenario, the very bad situation, and be prepared for that. But in operations, because planning engineer will never be able to predict exactly what can happen every day, right? So in the operation, operator need to utilize reliability standards and try not to intentionally violate any standard. They need to try their best to meet those standards. Although sometimes the violation do happen because the people can make errors, make mistake, and also there could be some failures of the measuring equipment, such as the operator cannot get the real-time data. For instance, in 2003 blackout, in the energy management system located in the control room, that collect all the data and do a pre-processing and show the data to the operator. But that system, the program of the system fail. So such as the operator cannot get real-time data. They don't know what was happening in real time. So that can happen. So, but they are not intentional violation. Okay. This is a large table that include all the contingencies or planning events that they need to be studied by the planning engineers when they design and plan for the system. The first column is a category. So you see they are numbered by P0, P1, and all the way to P7. If you rate the name after the number, so P0 means no contingency, right? That means a normal system. A normal system means all the equipment actually are in place and not disconnected, but system load may vary. So the planning engineer, they need to study any normal system change without loss of any element of the system. So that called P0. Starting from P1, then P1 is a single contingency. Single contingency is based on the normal condition, and you can just lose a single generator, single circuit, single transformer, or single shunt device. The fault type can be three-phase or could be a single line to the ground, right? So you really need to study on the high voltage usually means above 200 kV, and EHV means usually the voltage above maybe 300 kV. For such contingency, they should never interrupt the system operation, right? So you need to make sure in the planning stage, when you study P1, you just simulate all possibility of such a category, and then none of such contingency will cause interruption of the power. So that's the job of planning engineer. So continue, there's a more category. And if we give them an easier name to memorize, so P0 means N minus 0. N means the total number of elements the system has. N minus 1 means you just are going to lose a single element. So both P1 and P2 are N minus 1. They may have a slight difference if you look into the details. Starting from the P3 until P7, they're all about N minus 1. But N minus 2, sorry, but N minus 2, there are a different scenario. For instance, the P3 is N minus 1 minus 1. It is multiple contingencies. It's a loss of two components, but it's based on you assume you're already at the initial system condition. You already lost one element. That could be from P1, right? So it could be a condition from P1, then you'll add another contingency. So that's why this one is called N minus 1 minus 1. So this initial condition is already N minus 1. Maybe I need to use, instead of using positive 1, I need to use minus 1. Yeah. So the base condition, you lost one component, and then you have another single contingency. For the MS2, which means you are based on MS0, but the contingency will be losing any two of the components, right? So there are also other more detailed contingencies. So basically, by planning engineer, you need to simulate all such contingencies listed in this table, considering all the combination of the devices, component of your system. And now such contingencies will cause power interruption. So if you can finish all such study, you meet all such requirements, then your system is considered to be reliable from the planning point of view. In real-time operations, how this contingency really happen may cause some result different from the planning study, but that is from the operational perspective. Okay, so I think I don't have time to finish this one, but I only just maybe quickly talk about the idea, and we can finish these slides on Wednesday. So there are so many contingencies from n-0 to n-1 to n-1 -1, n-2. If you also include some extreme events, which means n-3 or 4 or more, right? So how do those contingencies distribute among the some figure? How can we visualize their differences? So we can draw this plot. The x is about the cost of the contingency, or we can call it the consequences. So when you see the consequences high, which means it will cost more. The y is the likelihood or probability. Okay, so for a power system which is well designed, the risk level, the risk of violation and the reliability need to be low enough, right? It should not be very high. So risk usually considered to be the product of a cost and the probability. So to maintain the risk level as low as possible, or at least considering the economical cost. So the risk level usually need to be on this hyperbolic line. Okay, so which means you may have some contingencies. The cost is very low, such as -1, right? But the likelihood is very high. Or you have some contingency such as a dream event. The cost is very high, but probability is very low. So if a system is designed well, all the contingencies align along this curve. The curve will have the constant risk, which is the product of cost and probability. So the contingencies we just talked about, starting from P0 and the P7, all the contingencies along this line. So P0 and P1, P2 are pretty much in this region, and then P3 to P7 for multiple contingencies are pretty much in this area. Okay. All right, so I will just stop here. We'll finish this slide on Wednesday. I will send notice depending on how whether campus will be open or not. So if the road condition is improved, so we may be able to meet in the classroom. Otherwise, we'll just use the Zoom. All right. Any question? Okay, so if no question, I'll see you on Wednesday.